at trig. So some basic revision, some stuff you would have looked at. SOHCAHTOA. Basic revision of what each of these is. So your sine theta is equal to the opposite over the hypotenuse. Cos theta is equal to the adjacent over the hypotenuse. Tan theta equals the opposite of the adjacent. Easy to remember. I'm pretty sure they actually are in your formula sheet as well, even if you don't remember them. But yeah, just some basic revision of the basis of trigonometry. It may seem super simple, but it does come up a lot, and you really do need to know your SOHCAHTOA. So please keep that in mind whenever you're doing some of your trig stuff. You actually will get a lot of questions specifically as you learn to do some of the harder stuff in trig. You're going to forget that SOHCAHTOA exists, and you'll get like questions on right angle trigonometry, and you're going to forget that you can just use SOHCAHTOA to do it, okay? So SOHCAHTOA does not become redundant once you learn to do non-right angle trig. So yeah, remember your SOHCAHTOA stuff. This is it. Just a bit of a practice question. If tan x is equal to 4 and 3, find cos x and sine x. So I'll give you guys just a minute to have a go at this one. Pause, skip ahead, do whatever you need to do to be able to do this question. Alrighty, so let's have a look at this one together. So a lot of this trig section of the lecture is going to be just about doing example questions. So hope you've got some paper in front of you. So if we've got tan x equals 4 on 3, this essentially represents the opposite over the adjacent. So we know our opposite is going to be 4 and our adjacent is going to be 3. So therefore, using Pythagoras' rule, in order to find the hypotenuse, we're going to have the square root of 4 squared plus 3 squared. So 4 squared is equal to 16, 3 squared is equal to 9. If you add those together, you're going to get 25. Square root them, you're going to get 5. So we can therefore say here our hypotenuse is going to be equal to 5. Therefore, cos x is going to be the adjacent, which is 3, over the hypotenuse, which is 5. And sine x is going to be the opposite, 4 over the hypotenuse of 5. So you're going to get 3 on 5 and 4 on 5 as the solutions to cos x and sine x respectively. It's actually a pretty common exam style question that you may get asked a bit. So make sure you're familiar with how to do this sort of thing, and make sure you're familiar with how to do it if I put negative 4 and 3 here or something like that. Alrighty, so the next thing we're going to look at, which you've probably been introduced to already, is the exact ratio triangles. So these are actually also in your formula sheet. This little snippet here is directly from that formula sheet. So essentially these exact ratio triangles are little triangles that allow us to find exact values when we're answering trigonometric questions. So you'll find that when you're doing this topic, specifically in year 11, a lot of your questions are going to begin with, using the exact value or, find the exact value of. And essentially what they're getting at is they want you to use these ratios to find exact values. Now, the reason that they're called exact is because a lot of them use surds. So essentially they're asking for like the non-decimal form of the surd. So I'm assuming you guys have been through how to find these ratios in class. If not, it's just using your basic SOHCAHTOA. For example, if we're trying to find the sine of 60 degrees, we're going to have the opposite, which is root 3, over the adjacent, which is root 2. and we get the sine of 60 degrees is equal to root 3 on 2 as the exact value. So you don't have to actually remember these ratios because they are in your formula sheet. Like I said, this exact triangles are there. But you also just have to know how to use them and what they mean when a question says find the exact value. Now, something I will say here is that just because a question does not say find the exact value does not mean you shouldn't. So if you end up with a question, you do some working, and let's say you end up with, this line of 60, like what does it equal? Do put the exact value in there as well, because they won't always specify that's what they want you to do. They're just going to assume that you know, unfortunately. So yeah, just because something doesn't say exact value doesn't mean you won't have to. So just keep an eye out whenever you're doing your trig questions about whether or not you have any of your sine, cosine, tan, 30, 45, and 60 degrees, whether they come up at all. All right, so the first big thing of non-right angled trig is the sine rule. So your sine rule essentially allows us to find unknown lengths and unknown angles in right angled triangles. And we use the sine rule if we are given one side and two angles and we want to find a side, or if we want to find an angle if we've been given two sides and one angle. Okay, so essentially the sine rule looks at this triangle, big A, big B, big C, and then we've got little a, little b, little c, and it's essentially relying on the fact that ratios exist in any non-right angled triangle. The length of A over the sine of big A is equal to the length of little b over the sine of big B, which is equal to the length of C over the sine of big C. And those ratios exist and hold true for any non-right angled triangle. So like I said, we want to use this when we've been given either two angles and a side or two sides and an angle. So we're going to look at some practice questions because I think the best way to work out and understand this rule is to look at practice questions. So this one comes from the HSC from 2006. It was worth 2 marks, and it says find the value of theta in the diagram. Give your answer to the nearest degree. So the reason that we know that we have to use the sine rule here is because we want to find an angle and we've been given two sides and an angle. Okay, so if we want to find something and we've been given one more of that thing, so we've been given one more angle and two more sides, then that's how we know we're going to be wanting to use the sine rule. So I'll give you guys a minute just to work out and see if you can play around with this a little bit to see if you can calculate what theta is equal to, correct to the nearest degree. So I'll give you guys just a minute. Again, you can skip ahead or pause if you're going to need more or less time. Okay, so when we're thinking about the solution here, we need to use our ratio that the length of A over sine A is equal to the length of B over sine B. Okay, so in this case, let's look at our diagram again. This angle is going to be sine A, and then our corresponding opposite, so direct opposite. Another way to think about this is the length of the side from which the angle does not touch, right? So you see this angle is formed by the length of this side and the length of this side, but the length that we care about is the one that it does not touch, okay? So if this is sine A, then 5 is going to be our little a. If we have sine of 33, then 9 is going to be our little b. Okay, so we'll end up with A equals 5, sine A equals sine theta, B equals 9, and then sine B is equal to sine of 33. Then we just substitute those into our ratios, so we'll end up with 5 over sine theta equals 9 over sine 33. Once we get rid of or move that 5 across to the other side, we're going to get sine theta is equal to 5 sine 33 over 9, which will equal sine, the inverse of sine of the 5 sine 33 of 9, so we can get that theta by itself. Then if you pop that in your calculator, making sure that your calculator is in degrees, something that goes wrong very frequently in your 11 and 12 trig is doing things in radians when you should do them in degrees, and doing things in degrees when you should be doing them in radians. But this question has asked us to find to the nearest degree, so we know we are in degrees, not radians. So if you pop this into your calculator, making sure it's in degrees, you'll end up with 17.61, rounded off to the nearest degrees is equal to 18 degrees. So it's pretty simple, just making sure you get these ratios right, okay? So if you're putting the side in the numerator, you've got to make sure you're putting the side in the numerator on both sides and your angles in the denominator on both sides. It actually doesn't matter if you put the sine in the angles in the numerator, so long as you do it on both sides. So this could also be written as sine A over A equals sine B over B, and you will still end up with the same answer. So long as you're doing it to both sides, the ratio will remain the same. All right, looking at a second question using the sine rule. This is from the 2002 HSC. So in the diagram, XYZ is a triangle where Z, Y, X is 45 degrees and Z, X, Y is equal to 60 degrees. Find the exact value for the ratio X over Y. This is a little bit trickier and it's worth 3 marks. So I'll give you guys a minute to have a look at this. Again, feel free to skip ahead or pause the video. And if you're watching live, feel free to pop your answer in the chat as well to get some feedback, or ask any questions in the chat if you've got them as well. Alrighty, so hopefully you guys are having a go at this. I'll give you guys maybe 30 or 40 more seconds. Again, feel free to pause it if you do need more time. So these questions are super common in the HSC as well. So not just year 11, but you do need to know how to do these in your HSC as well. Okay, so we're gonna have a look at the answers. So if you're not ready for the answer, pause the video here. Otherwise, we're using our ratio again. So this time we're just gonna do X's and Y's instead of A's and B's. Doesn't really matter. So we're going to have little x over the sine of big X equals little y over the sine of big Y. So we're thinking about this. Sine of big X equals sine 60, right? Because if we're looking at our example here, the sine of our big X is sine 60. Then sine of the big Y is equal to sine of 45. Okay, so it's just that one over there. Then when we're thinking about our exact ratios, okay, anytime you see 60, 40, or 30 attached to sine, cos, or tan, we're thinking about our exact values, our exact ratios. Okay, so sine of 60 is equal to root 3 on 2. Sine of 45 is equal to 1 on root 2. These are on your formula sheet in those little triangles, so you don't have to stress about remembering them. Although I will say with enough practice, you do sort of start to just remember what they are. Then from here, what we want to do is we've got x over root 3 on 2 is equal to y over 1 on root 2. Because what we're doing is, if we know that sine 60 is equal to root 3 on 2, we're substituting that into our equation. So we've still got little x on top, and we know what sine x is equal to. So we've got little x over what we know sine x is equal to. Okay, same thing on the other side, little y still on top. We know that sine of y is equal to 1 on root 2, so we're putting that in the denominator. So therefore we can say that x on y is equal to root 3 on 2 multiplied by root 2 over 1. And then we just end up with x on y is equal to root 6 on 2. Okay, so this question isn't too tricky once you remember that you do have your exact values that you can rely on for any question to do with 60, 45 or 30 degrees and either sine, cos or tan. Okay, so just remembering that those ratios exist is so super important, as you can see, because this question would be pretty much impossible to do if you didn't remember what those ratios were. Okay, so that's it for the sine rule for today. Next is the cosine rule. So just like your sine rule, the cosine rule allows us to discover properties of non-right angled triangles, and it uses the same sort of triangle with your angles being represented by your capital letters, sides being represented by lowercase letters. So our cosine rule is equal to a squared equals b squared plus c squared minus 2 times b times c times cos a. I've written that a bit of a weird way because on your formula sheet it's given to you as c squared equals a squared plus b squared minus 2 times a times b times cos c. I mean, it's the exact same thing, just using different letters. So we've got a squared equals b squared plus c squared minus 2 times b times c times the cos of a. The big thing to remember here is that you just have to make sure that if you're doing a squared here, so this side, you do the corresponding angle, so the opposite angle to this side. So we're using the cosine rule when we need to find the third side if we've already been given two sides and an angle, or if we've been given all three of the sides and we need to find an angle. So just like the sine rule, I think this is easiest to understand when we look at some practice questions. So this is from the HSC question as well. I think this was worth maybe 2 or 3 marks. So in the diagram, AC, which is this one here, is parallel to DB, which is represented by these little arrows. AB is 6 centimeters, BC is 3 centimeters, and AC is 7 centimeters. Use the cosine rule to find the angle ACB correct to the nearest degree. Okay, so this one, it's been nice to us. It's told us that we need to use the cosine rule. But even if it didn't tell us that, and it asked us to find the size of angle ACB, we would know that we have to use the cosine rule because we've been given all 3 sides and we've been asked to find one angle. Okay, so if you've been given all 3 sides and the question asks you to find an angle, should be alarm bells going off that we're using the cosine rule. So I'll give you guys a minute just to have a go at this one, and then we'll go through the answer together. Alrighty, so first thing we want to do is we want to rearrange our equation so that we can get the cos of C by itself, okay? So we want to get this bit by itself. So we just rearrange our equation, which I think they actually give to you on your formula sheet if I'm not mistaken. Otherwise, just rearrange it like you would any other algebraic equation, and you would get cos C is equal to a squared plus b squared minus c squared all over 2ab, okay? we need to get this cos C by itself because we're trying to find this angle C. So then we've got cos C equals 3 squared plus 7 squared minus 6 squared, making sure that whichever side you're subtracting is the one opposite the angle you're trying to find. Okay, so we're trying to find this angle, so the side we are subtracting has to be the one opposite to that. Okay, so then we get 3 squared plus 7 squared minus 6 squared over 2 times 3 times 7. So we'll get cos C is equal to 22 over 42. Then we just take this cos across by making an inverse, and we'll get that angle C is equal to cos to the negative 1 of 22 and 42, which if we put that in our calculator, making sure it's in degrees, we'll get 58.41. Rounding off to the nearest degrees, we get 58 degrees. Okay, so again, this is just another rule that you pretty much just have to substitute things into an equation, so not too tricky. And then we're going to do this practice question as well, which is from the 2001 HSC, and it's worth 4 marks, which is like fairly hefty for a HSC question, because if you think about it, like 4 marks is like 1/25 of the paper. So you don't go around giving 4-mark questions out too often. Okay, so the diagram shows a triangle with sides 7, 13 x centimeters and an angle of 60 degrees is marked. Use the cosine rule to show that x squared minus 7x equals 120, and hence find the exact value of x. Okay, so again, it's been quite nice to us. It's told you that you need to use the cosine rule. Otherwise, if it didn't tell you that, you would know you need to find the cosine rule because it's given you 2 sides, an angle, and it's asked you to find the third side. Okay, so I'll give you guys maybe a minute and a bit just to have a go at this question because it is a bit tricky. And I just want you to think about it before we go through it as well. So again, if you want to go straight to the answer, skip ahead, otherwise pause it and have a go. Or I'll give you about a minute, so see how much of it you can get done before we go through it together. Right, so we might have a look at this question. So with this, our cos rule, a squared equals b squared plus c squared minus 2 times b times c times the cos of a. First thing we want to do is just substitute in everything that we know. Okay, so we've got 13 squared equals 7 squared plus x squared minus 2 times 7 times x times the cos of 60. First thing to recognize here is that x is not the side associated with your angle. I think a lot of people tend to innately think that when you're being asked to use the cosine rule, that whatever side is marked with the pronumeral is the one that is going to be using the angle. But in this case, we've got to recognize that this angle is opposite from the 13. Okay, so in this case, our C is actually going to be 13 because C is whichever side is opposite your angle. Hence, we've got 13 squared equals 7 squared plus x squared minus 2 times 7 times x times cos 60. Now, I did just say C because I'm really used to thinking of it as C, but in this case, with the way I've written it, it is A. Anyway, so then we get 169 equals 49 plus x squared minus 14x times a half. A cos 60 equals, as cos 60 equals a half, which is why we get this half here. Because again, we're remembering that our cos 60 is an exact value, which we know is equal to a half. Okay, so then you get 2 times 7 times the x gives you the 14x times the half. So then once you've done that, if you subtract that 149 across, and then multiply the 14x by the half, you'll get x squared minus 7x equals 120, which is the first thing that they've asked you to find. Then in order to find x, we've got a quadratic. So move that 120 across, you'll get x squared minus 7x minus 120. Factorize that out, you'll get x minus 15 times x plus 8 equals 0. Therefore, x is equal to 15 and negative 8. Now, this is super important because usually in the HSC, marks are actually associated with discounting the solution. So you therefore say, however, because the length can't be negative, x is only going to be equal to 15. So it's super important that if you're going to discount that one, you know you have to discount the solution. And two, if you're going to discount it, that you give a reason as to why you have discounted it. Okay, so our length can't be negative, so therefore we can't have negative 8 as a solution. And so yeah, that's about it for cosine rule. It's again like the sine rule. The sine rule and the cosine rule and the area of a triangle, which we're about to look at, are all pretty much just about substituting things into a formula. So they're not too tricky, so they're good questions to get in your exam. So then area of your triangle allows you to find the area of a non-right angled triangle. Again, on the basis of this same triangle where your capitals are your capitals are angles, your lowercases are the lengths of sides. So your area, so this A is not equal to this A. This A stands for, let me see if I can write it, area. So area equals a half times A times B times the sine of C. So it's pretty easy. So we'll just have a look at a quick example question from the 2002 HSC. So I'll give you just a minute to have a look at this one. So in the diagram, LMN is a triangle where LM equals 5.2 meters, LN equals 8.9 meters, and angle MLN is 110. And so for 2 marks, calculate the area of the triangle LMN. The reason you know you have to use the area of a triangle formula is because it's literally told you to find the area and it's not right angled. So you need to use the formula for non-right angled triangles. Okay, so I'll give you just like a minute to have a quick go at this one. Alrighty, so again, this is not too tricky. Area of a triangle is just about substituting things into a formula. So our area equals half times A times B times sine C. So therefore the area of LMN is equal to a half times M times N times sine L. Recognizing here that you've got the two sides and whichever side you're not multiplying, that's the angle that you use. So then area is equal to a half times 5.2 times 8.9 times sine of 110. So your area is going to be equal to 21.7 meters squared. Okay, and that's all you've got to do for that. So just, yeah, a little FYI. A lot of your trig is just about remembering rules and knowing how to apply them. So sorry about the spam that's happened and that we're about to go through, because it is pretty much just about remembering rules and knowing when and where to substitute things in. So we've been over sine, cos, and tan. Just another thing to sort of note, tan can also be expressed as sine over cos. And the reason that this is important is because it comes into play when we are looking at our reciprocal trig functions. Okay, so we've got cosec theta equals 1 over sine theta, so that's the hypotenuse of the opposite. Sec theta is 1 on cos theta, so the hypotenuse of the adjacent. And cot theta is equal to 1 on tan theta, which is equal to the opposite of the adjacent, which can also be written as the reciprocal of the 10 we just looked at. So cot theta can also be written as cos theta over sine theta. So these are all your reciprocal trig functions. So pretty much you find them by just, flipping your normal trigonometric functions around. They are actually also written on your formula sheet, I'm pretty sure, so you don't even really have to remember them. So just knowing that they exist, that they're there, and when you see them in questions, recognizing that cosec is the reciprocal of sine, sec is the reciprocal of cos, and cot is the reciprocal of tan. It's pretty much all you need to be able to remember. And then from there, if you know that cosec is the reciprocal of sine, you know it's going to be hypotenuse over the opposite, and then the same for each of the following ones. Something else to know with trig is about trig identities. So looking at how to prove cos squared theta equals sine squared theta equals 1 is actually one of your syllabus points. I'm going to say it's going to be pretty unlikely that you're going to be asked to actually prove this. I've never personally seen it in a question, but it is in the syllabus, so you do need to know it. And then from that equation, you can then derive the second of the trig identities, that 1 plus tan squared equals sec squared theta, and 1 plus cot squared theta equals cosec squared theta. Now, this identity here is on your formula sheet. These two are not, so you do have to know them. And they are super, super, super important to know for when you get questions about trig identities. So we'll have a look at some of those example questions in a little bit, but just knowing that they're there for now is enough. So to prove it, our sine theta is equal to the opposite of the hypotenuse. So if we rearrange that, we can say our opposite side is equal to the hypotenuse times sine theta. Then if we've got cos theta, we're going to have the adjacent over the hypotenuse. So we can therefore say that the adjacent is equal to h cos theta, so the hypotenuse times cos theta. If we then use Pythagoras to do a squared plus o squared, so adjacent squared plus opposite squared equals hypotenuse squared, we'll get h cos theta squared plus h sine theta squared equals h squared theta, which you end up with h squared times cos squared theta plus h squared times sine squared theta equals h squared. Divide all of those things by h squared, and you end up with your cos squared theta plus sine squared theta equals 1. So like I said, I think it's unlikely that you'd actually ever get asked to do this, but it's not too tricky of a proof to understand. So it is worthwhile knowing, and I think it also does help you just with a general understanding of what's going on. So let's have a look at some practice questions. So I think trig identities questions are probably for me was the hardest part of year 11, both trig and maths in general. So let's have a look at this question, which says sec squared x plus sec x tan x equals 1 plus sine x on cos squared x. So we're being asked to prove this question. So how can we prove that the left-hand side is equal to the right-hand side? So you guys may not have seen trig identities questions before, so I'm just going to go through this first one with you. So essentially, in order to do this, all you need to do is prove that the left-hand side is equal to the right-hand side of your equation by just manipulating things in between. So the left-hand side is equal to sec squared x plus sec x tan x. And so that's like literally what the left-hand side is equal to. We haven't changed anything there. So then sec squared x is the same thing as writing 1 on cos squared x, because that sec squared x is just the reciprocal of the cos. Then we can write sec x as 1 on cos x, and then multiplied by tan x, so this dot represents a multiplication, and then tan x is just sine x on cos x. So then once we do all of that, when we multiply these together, we would get sine x over cos squared x. So if we've got 1 on cos squared x plus sine x on cos squared x, add those two fractions together, we get 1 plus sine x all over cos squared x, which is equal to the right-hand side. And so that's all we need to do to prove that equation. So you guys have a go at these ones. So let's maybe give you guys a minute or so, have a go at part A, and then part B is tricky, so we might do part B together. So if you guys have a go at proving that sec squared theta minus tan squared theta equals cosec squared theta minus cot squared theta. Honestly, these are really hard, but they just rely on the fact that you know about your trig identities and what your reciprocal trig values are equal to and things like that. So have a go, remembering that you've just learnt this stuff. So if you can't do it or you're a bit confused, don't worry about that. Because honestly, you've just learnt it and you have so much time to perfect it. Okay, so let's have a look at these ones. If we've got sec squared theta minus tan squared theta equals cosec squared theta minus cot squared theta, let's first look at our left-hand side. And we've got sec squared theta minus tan squared theta. And then if we use the identity that 1 plus tan squared theta is equal to sec squared theta, so we just substitute 1 plus tan squared theta here, we'll end up with the fact that the left-hand side is equal to 1. Okay, from there, let's look at the right-hand side. So if we've got cosec squared theta minus cot squared theta, let's use the identity 1 plus cosec squared theta equals cot squared theta. Just pop this into our equation here, and we'll get the right-hand side also equal to 1. So therefore, left-hand side is equal to right-hand side, and we've just proved that identity there. So that's why it's really important that you know these identities, because they're not on your formula sheet. They are unfortunately just something that you do have to memorize. And so I'll go through part B as well. So if we've got 1 plus cot theta over cosec theta minus cos theta equals sec theta over tan theta plus cot theta, let's start by looking at the left-hand side. So we've got 1 plus cot theta over cosec theta minus cos theta. Then let's think about the fact that cot can also be written as cos theta over sine theta. Substitute that in and we'll get 1 plus cos theta over sine theta. Then think about cosec can also be written as 1 over sine theta, and then we don't change that cos theta. If you're ever stuck on these questions and you do have reciprocal trig values, just try putting in their sine, cos, and tan values, and you'll usually get a bit of an indicator as to where you need to go. Then once we expand all of that, we'll get 1 plus cos theta over sine theta times sine theta minus cos theta. Multiply these brackets by the sine theta, and we'll end up with sine theta plus cos theta minus cos theta equals sine theta. Okay, so the left-hand side is equal to sine theta. Then our right-hand side, we've got sec theta over tan theta plus cot theta. So we can also write sec as 1 on cos theta. We can also write tan as sine theta on cos theta. We can also write cot as cos theta on sine theta. Then moving these and making this denominator just into one fraction, we'll get sine squared theta plus cos squared theta over sine theta cos theta. Then we'll get 1 on cos theta multiplied by sine theta on cos theta on 1. Essentially because in order to get rid of this fraction in the denominator, what we do is we flip it and we multiply it by the numerator. And then we get 1 here because sine squared theta plus cos squared theta equals 1, because we know that we just proved that identity. So that was the identity that we proved just here. So we'll end up with 1 on cos theta times sine theta cos theta on 1 equals sine theta. So therefore the right-hand side equals sine theta and the left-hand side is equal to the right-hand side. And then that is all we need to do for that. Now that last trig proof was actually really hard. So if you're a little bit confused by it all, don't stress because it was really hard. And you have a lot of time to learn these as well. So what I'd recommend is that after you do trig identities in class, or when you feel a little bit more confident with them, come back to this lecture, come back to the slides, have a go proving those identities again, and you'll have to see like how much you've grown as well in maths so far. So that's